One of the key devices used in physical therapy is the parallel bar, commonly applied for improving gait and balance during early-stage rehabilitation. Its structure must be strong and safe under various loading conditions. For this project, we chose user weight as the main parameter as it significantly affects stress, strain, and deformation in the bar. A simplified 3D model was developed using SolidWorks to simulate how different adult weight categories such as underweight, normal, and overweight impacts the structure. These results were then compared with manual calculations to evaluate structural safety. This approach ensures our design meets clinical safety standards.
The objective of our project is to apply solid mechanics in a real-world biomedical context. We designed a simple parallel bar using SolidWorks to support users with different body weight, especially in rehab and physiotherapy setting. We also tested how the bar reacts under various weight in terms of stress, strain, and deformation. Finally, we compared the simulation result with manual calculation to make sure the design is safe and reliable. This is the engineering drawing of our parallel bar design. It shows the full dimension and structure we create using SolidWorks before running any simulations.
The design of the parallel bar was carried out in 3 main stages, involving the creation of the base with pillars, the handrails, and the final assembly. In the first stage, a rectangular base with dimensions of 3010 mm as length, 830 mm as width, and 50 mm as height was modeled. 4 cylindrical pillars were then extruded near the corners of the base. Each pillar has a diameter of 50 mm and a height of 1250 mm, serving as vertical supports for the handrails. The second stage involved the modeling of the handrails. Each handrail was designed as a cylinder with a length of 3010 mm and a diameter of 60 mm. 2 slots were then created along the handrails with a depth of 30 mm to accommodate alignment of the pillars. In the final stage, the assembly of the base and handrails were performed using SolidWorks assembly. The handrails were carefully positioned above the pillars and mates were applied between the inner slot faces of the handrails and the outer surfaces of the pillars, forming a complete parallel bar structure ready for simulation analysis. The type of material used is alloy steel. This is the properties of the material.
Here, you can see the parallel bar before and after applying the load. The visual shows how the structure deforms slightly when force is applied, simulating the real-life pressure from a user. The slide shows the simulation result for an underweight user around 50 kilograms. The stress, strain, and displacement are all relatively low, indicating that the design handles lighter users safely. For a normal weight adult, the structure shows slightly higher stress and displacement value, but still within the safe limits. This confirms the design worked effectively for average users. For the heaviest case, the stress and deformation increased significantly. However, the design still holds up, and the displacement remains under 1 mm, which is acceptable for a rehabilitation device. To conclude the simulation part, as the user's weight increased, the stress, strain, and displacement also increased. However, all results remain within the safe and acceptable limits, meaning the parallel bar is structurally reliable across different weight categories. This proves that our design is suitable for a wide range of users from underweight to obese.
Hi, Assalamualaikum. I'm ISKANDAR. So for the analysis of my manual calculation part, I'm going to explain about the first parameter, which is 50 kg weight. So as we can see, based on the manual calculation, we already get for the unknown force for the first one, which is A1Y, we got 245.25 Newton. And for the moment part, for 0 equal to 0 meter, we got a moment equal to 0 Newton meter. And for the 0 meter and 1.505 meter, the moment we got here is 738.2 nanometer. And for the agent load, for the displacement of A1, basically displacement of A1 and displacement of A2 is equal, and we get 7.434 power multiple 10 power of -7. And as you can see, we get for the graphical diagrams, Here I already put the shear diagram and moment diagram.
Force with 70 kg. Firstly, we need to draw the free body diagram and then find the reaction force on AY and BY. Next, we need to find the shear and the moment while x equal to 0 and x equal to 1.505. For x equal to 0, V is 343.85 and the moment is 0. And then for the x equal to 1.505, V is 343.85 and the moment is 517.49. For the second section, at x equal to 1.505, V is negative 343.85 and the moment is 517.50. And then at x equal to 3.01, V is the same and M is 0. And we need to calculate the displacement by using axial load, which the formula is PL over AE. And then we got 1.04 times 10 power of negative 6. And the last one is for stress. The formula is P over A, and we got 175.12 kilopascal. For the force with 120 kg, we need to draw the free body diagram and find the reaction force on AY and BY. Next, we need to find the shear and the moment, while x equal to 0 and x equal to 1.505. For x equal to 0, V is 590.56 Newton and M is 0. For x equal to 1.505, V is the same and M is equal to 888.8 Newton meter. For the second section, at x equal to 1.505, V is negative 590 and the moment is 888.8 Newton meter. And at x equal to 3.01, V is the same and M is 0. And again, we need to calculate the displacement by using axial load, which is the formula is PL over AE. We got 1.79 times 10 power of negative 6. And the last one is for the stress. The formula is P over A. We got 300.77 kilopascal.
For the comparison result part, based on the parameters given, for the first one, 50 kg, the value from SOLIDWORKS result and manual calculation result have a little bit difference for strain, displacement and stress. Same goes with the 70 kg parameter. It also have a different value between SOLIDWORKS result and manual calculation result. For the strain, same goes with displacement and stress. And for the last parameters given is 120 kg. It also have different value from SOLIDWORKS result and manual calculation result.
So for the conclusion, we simulated parallel bar under 3 load conditions, which the first one is 50 kg, second one is 70 kg, and the third one is 120 kg. And then we also compared the simulation result with manual calculation to ensure our accuracy. And then we also find out that heavier load cause higher stress and greater displacement. And then we also analysis show how load variation affect the structural performance. And then last one is we gain a valuable insight into design consideration for safe rehabilitation equipment.